All right, folks, this is lesson 10.3 we did in class today. There's not a whole lot I want you to take away from this lesson. There's a couple little things. We'll go through it because the book does, but it's not a huge takeaway from this, this chapter. So we're looking at applying theorems about chords. We should be able to use chords of circles to find arc measure, use chords of circles to find lengths, describe the relationship between the diameter and a chord perpendicular to the diameter is kind of the big one. Find the center of a circle given 3 points on the circle. We've really already done that in our triangle chapter. So we want to just recall here that a chord is the segment with the endpoints on a circle. Because its endpoints lie on the circle, a chord divides the circle into two arcs. Sometimes it divides it into a major arc and a minor arc. If that chord happens to be a diameter, it divides the circle into two semicircles. If it's not a diameter, it divides the circle into a minor arc and a major arc. And we've talked about that already. This is kind of just a goofy little theorem that says if we're in the same circle or two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So in other words, these chords are congruent because their arcs are congruent. Conversely, the arcs are congruent because the chords are indicated as congruent. That makes sense to us because if we had two different size chords, if there was a chord that went from here to here, the arc that it creates would be a different size from this arc. So chords are congruent if the arcs are congruent if their chords are congruent within the same circle. One of our takeaways, kind of an interesting thing to know, and we should probably keep this in mind. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and bisects the arc. So we've got a diameter that's perpendicular to a chord. And what happens then is that that chord is bisected, only if that chord is perpendicular to the diameter. In other words, if I had another chord over here, it's not perpendicular. That diameter or that chord is not bisected by the diameter. That happens only if that diameter is perpendicular to the chord. Not only does it bisect the chord, it bisects the arc as well. So it kind of makes sense when we think about it from the opposite point of view. If it's not perpendicular, it wouldn't bisect. It only bisects if it's perpendicular. We can kind of get here's a little mini proof. That would form two isosceles right triangles because the radii are congruent. And with isosceles right triangles, the altitude to the base bisects the base. And then the converse is also true. If one chord is the perpendicular bisector of another, then the first chord has to be a diameter. If we had another chord that was perpendicular to a given chord, but didn't bisect the original chord. So in other words, this piece is not the same length as this piece, then clearly it's not going to be a diameter. So just a couple of notes about diameters being perpendicular to chords. This is kind of a goofy little exercise. We've got two different circles, and we have to notice within the circle that we have this notation. Those two radii are congruent, which means the circles are congruent. We have this notation, meaning the chords are congruent. It says find the measure of arc FG. Well, arc FG is in a circle that has no markings in it. But if I go to the other circle, I notice that arc JK is 80 degrees because these circles are congruent and their chords are congruent. Arc GF or FG would also be 80 degrees. So look for those markings within a diagram. We have, like we have all year, kind of study what we're given in that particular information. My dog just came up and is staring at me and wants to do geometry with me. Everybody say hi to Pi. There she is. There's her Pi on her chest. So again, the thing that we learned about this idea of, again, staring at the picture, I recognize that the diameter is perpendicular to a chord. And what that told us is that the chords are congruent. So if I look at this particular question, this one's saying find the length of HK and find measure of arc HK. So HK is from here to here. I notice I'm given these two things, 70 plus x and 11x. And because our chord is perpendicular to the diameter, I know that 70 plus x has to equal 11x. That gives me 70 equals 10x, so x would equal 7. And if x equals 7, this piece is 77. Also, this piece is 77, which tells me that arc HK happens to be 154 degrees. And that's by adding the two of them together. I'm also asked to find the length of HK. And if I, again, look at the picture, I'm given specific information. I'm given that KN is 7 because that diameter is perpendicular to the chord. That means this piece is also 7, which means that HK is 14. So it's little pieces of information. Chord perpendicular to a diameter makes things congruent or equal. This is kind of a silly question. Again, we've already done this in terms of triangles. It says 3 bushes are arranged in a garden as shown. Where should you place the sprinkler so that it's the same distance from each bush? And what we talked about before is finding a point that's equidistant from the sides of the vertices of a triangle. And we did that by looking at the perpendicular bisector of all those sides. Well, we can kind of do the same thing here, except just talk about the perpendicular bisectors and how that relates to a circle. If we look at the perpendicular bisectors of this side, I'm going to just kind of sketch it in. We could use our compass or protractor and straight edge, compass and straight edge, to find that perpendicular bisector. Perpendicular bisector here would kind of go like this. How this relates to circles is that we could talk about a sprinkler. We could put a sprinkler here, a circular sprinkler. And once we find that point of intersection of those perpendicular bisectors, that sprinkler would sprinkle water, spray water equidistant, including all 3 of those bushes. Let's see, we got this equidistant chords theorem is kind of the other big takeaway from this section. Equidistant chords theorem says that if we've got the same circle, or we have 2 congruent circles, 2 chords are congruent if and only if they're the same distance away from the center, if they're equidistant from the center. And what we have to remember is that we measure distances perpendicularly. Remember that there are lots of distances from that center to the chord. But if we're going to talk about specifically giving a distance, naming a distance from a point to a line, we talk about the perpendicular distance. And what this theorem says is that if these 2 chords are congruent, then their perpendicular distance from the center has to be the same. If I drew another one over here that was equidistant, the same distance or the same length as CD and AF, its perpendicular distance from the center would also be the same. It tells us a little bit, it's kind of interesting. Let's see where that takes us in terms of trying some questions. So here's our diagram. It says in the diagram QR equals ST equals 16. So QR is 16. ST is 16. Find the radius of the circle C. So as I'm looking here, I notice that the diameter WX is perpendicular to QR, which tells me that UR is 8, QU is 8. I know that because of that theorem we just mentioned, the perpendicular distances from the center are the same because those 2 chords are the same. So I can say 2x is equal to 5x minus 9. And solve for x. If I subtract the 5x, that's minus 3x equals minus 9. So x would equal 3. It's asking, though, for the radius of circle C. And I've not got the radius yet. Let's see what I can find out. If x is 3, 2x is 6. So this piece is 6. This piece is also 6. But it's looking for the radius. The radius is not really drawn in here, and a lot of times it helps us to draw a radius. And I'm going to draw a specific radius. I'm going to draw a radius like this. What we have to get used to is kind of drawing it to the best possible point. And now what I have is a right triangle, URC, and its sides are 6 and 8. Its legs are 6 and 8. A little Pythag gets me that CR is 10. So our radius of circle C is 10. So there was a lot going on within this question. First of all, we had to recognize that the two chords are congruent and they're each 16, as we were told, which gave us that this piece was 8, this piece was 8. We don't know that these were both 8 because that diameter is not perpendicular to that chord. But we do know, because those two chords are congruent, that their distances away from the center would be congruent. So this 2x is the same as this. We can then solve for x. Then we can find this length, and then we can add in the diameter, the radius, and that would give us the radius by a little bit of Pythag. So go over to Schoology, and we're going to do page 531, numbers 1 through 8 and 11 through 14 for homework tonight. You can refer back to these last few questions if you need to. All right, hope the AP went well, and we'll see you tomorrow. Bye-bye.